This video is on two sample t-tests, which is very, very similar to all of the other tests that we've done, following the same procedure. I've noted a couple of differences for you. I'm only going to do one example for you in this video, and I'm going to be on the last page of your notes the whole time. There was nothing else to write on page 19. So if you're following along with me, I'm on page 20 with this problem about a blood pressure medication. But before I jump into that, I do want to talk to you about the main differences that you see between two sample tests for proportions and two sample tests for means. And they're all over here on the left side of your screen. This is a test. We're still using that phantom step acronym to go through our 8 different steps to perform this test, but there are a couple of differences for means that didn't show up in proportions. Okay, so the first one is in the hypothesis step, which I'm hoping you're like, okay, duh, Miss E, right? So our null hypotheses are written with means instead of proportions. Null and alternate hypotheses are written with means instead of proportions, just like with the intervals, right? We're writing these with means instead of proportions because this is T. T goes with means, right? This is a difference of means test. A two sample test is always a difference test. You're subtracting two populations. So that means your null is always going to be equal to 0. But this time it's mu1 minus mu2 instead of p1 minus p2. But this is your null. Always, always, always if you're doing a two sample t-test. Second change is that you have to check the conditions twice. Right? So both populations have to be drawn randomly, or it has to be randomly assigned to two different groups, for example, right? You have to check the 10% condition for both groups, and you have to check the success-fail condition for both groups. So same conditions, just check them twice. Okay. The success-fail condition, remember that's different from proportions. So the one for proportions is really, really long and complicated, right? You have to do P times 1 minus P, or NP, 1 minus P. Sorry, that was the standard deviation. It's a little late at night for me. So for the success-fail conditions for proportions, that was unit 7, you would have to do NP and N1 minus P, and you'd have to check to see that they were both greater than or equal to 10. It's not the case for means. Remember, it's a lot easier for means. You just have to check to see if the population is normal or if both sample sizes are greater than or equal to 30. Remember, okay, even if both of those are not satisfied, as long as you look at the data and there's no obvious outliers or skew, like there's not one very, very obvious outlier, or the skew is not really, really, really obvious, then you can continue with the test. On the actual AP test, you will be able to continue doing the test, right? They're not going to do a free response question where you just can't do the test, right? They're not going to do that because that would be dumb. Okay? Some of the labs that we've done, because we're generating the data ourselves, do have a little bit of skew in them, which some of you have been emailing me about the past couple of days. Okay, so that's your success-fail condition change. And then your standard deviation formula is different. Obviously, there's no proportions. You don't have to do any multiplying. I'm hoping that this looks very, very familiar to you because you saw it in the last video. It's the exact same formula that we used in the last video for confidence intervals. The one thing I want you to notice is that there is no pooling. So take a second, think back to unit 7 when we first did these two sample tests for proportions, and I told you that you had to take your first population proportion and your second population proportion and combine them somehow. And the way that we did that is we found a new proportion, a combined proportion called the PC, and it was written like, it was written like this. It was this one, PC, right? P hat C. So remember, you had to combine x1 plus x2. Oh dear, I've gone offline. Whoops, I'm hoping that fixes itself momentarily. Okay, you'd have to do this, x1 plus x2. over N1 plus N2. And that's what you would use here for both populations. You do not have to do that for means. How lovely and exciting for you. You can just use this exact formula exactly as it is written. You don't have to calculate anything new. Okay, I have to pause this video momentarily because I think my Wi-Fi has gone out. So that's kind of a problem. Give me a sec and I'll be right back. All right, back at it again with the working internet. Fixed my internet. Sorry. This is the struggle that we're living in COVID-19, man. If your internet dies, then you are out. It's not it. Okay. All right. So let's get back into this 2-sample test. Like I said, I'm only going to do one example for you. I'm hoping that at this point we have run so many tests, so many hypothesis tests that you're pretty familiar with the whole process at this point. But I do want to do at least one example for you. So in this example that we have going on here, this is about a blood pressure medication. Okay, so what they're trying to figure out here is my blood pressure medication that deals with, it's a calcium pill in this problem. They're checking to see if this calcium pill reduces blood pressure more than the placebo pill. This is a very typical thing that people do in medical studies. One thing that I would like you to notice is this right here. It says an increase in blood pressure appears as a negative number. So if I want my calcium pill to work, I want big positive numbers because that means a big reduction in blood pressure. So for example, this number right here, the 18, that's looking good for the calcium pill. That is a large decrease in blood pressure. This number right here, the 1, not so hot, that's a very small increase. And this, for example, that's really what I don't want. If I want my calcium pill to work, then I don't want negative numbers, I want positive numbers. A negative number is an increase in blood pressure. So that's no bueno. That's not what we want. Okay, again, and then before I jump into this whole test, I want to point out to you again why this is not paired. If you go up into the actual scenario, it said there's 21 healthy Black men who volunteered to take part in this experiment. There was no way to group those men or to easily pair those men. They were not siblings. They were not from the same family. We don't know if they were from the same area. If they had similar health issues. They also didn't have each person take both pills in a random order. So like when we did the hallway bowling, each of you was a pair there because you bowled with both hands, your dominant and your non-dominant hand. You bowled with them both, so you were the pair. That's not the case in this study. Each of these men only took one of the pills for the entire time. So this is not a test that you can easily pair. Another tip for you is if you look at the data, see how there's this one that's kind of hanging out by itself. In paired data, every number in one group will have a number that goes with it in the other group. So definitely not paired. All right. So let's get into this test here. We're still following our phantom steps. I'm not going to write out every single thing for you on this side of the screen, on the right side of the screen, because I do have all of it written out for you here on the left side of the screen. So just make sure you're following along with me in both places. So here, the question is, do the data provide convincing evidence that a calcium supplement, so that's the calc at the top, reduces blood pressure more than the placebo? So for my P step, my phantoms, my parameter is we are examining true mean difference in blood pressure decrease for the calcium supplement and placebo. And in this case, let me switch to my pen. Again, you want to make sure, like I said in the last video, please, please, please make sure that you are identifying your variables. Okay. So your calcium supplement here, I'm calling it mu sub C, and the placebo, I'm calling mu sub P. Just so I can keep it straight and so that the AP readers know what the hell I'm talking about. Okay. All right. So then let's proceed to our hypothesis step, my H step. So for this one, remember you need your null hypothesis and your alternate hypothesis. So my null hypothesis always is I'm going to subtract these, mu sub C minus mu sub P, because I remember what I really care about is how this performs, the calcium supplement. So usually a good idea to put that one first, and then subtract the placebo. My null hypothesis is always that the difference is 0 here. We are assuming that the calcium pill does no good and or no better than the placebo, and we are trying to prove otherwise, right? So my alternate hypothesis is mu sub C minus mu sub P, and then I have to figure out, okay, do I want to see if it's greater than 0, less than 0, or not equal to 0? So if I go back up to the question, it's, do the data provide convincing evidence that a calcium supplement reduces blood pressure more than the placebo? So that means we are saying these numbers are bigger than these numbers. That's what we're trying to prove. So we're going to say that this is greater than 0. So if it should have been a less than symbol there, this would have said less than the placebo. If it was a not equal to, this would have said different than the placebo or not the same as the placebo, and it wouldn't have indicated a direction one way or the other. So that is your H step right there. Sorry if you can hear the crazy scraping. I'm having to put my mouse on top of a suitcase. So it's making some crazy sounds here. All right, so let's look at the A step next. And again, I'm not going to write all of these out because I do have them written for you on the left side. So I'm just going to say here, see slides on the left, but I'm going to talk you through these. So this is not a sample because it talked about how these men volunteered, but it did say that they were randomly divided into the 2 groups. So it's a randomized experiment. So check, that's my randomness condition. Second, I have to check my 10% condition. So that's 10N, so 10 times the sample size, and I want that to be less than the population. So if you look over here to the left, this one at the top is for the calcium group because there were 10 people in that group. So 10 times 10 is 100, which is definitely less than the total number of healthy Black men, which is the population for this study. And then this second one here is for the placebo. So there were 11 people in the placebo groups. That's 10 times 11, which is 110. Again, less than the number of total healthy Black men in this population. So different slightly from the last example that I did for you with the interval, because for the interval, both sample sizes were the same. So I only had to technically check this once and just say, like, add an and after here to say for this population and this population. But for this one, since they have 2 different sample sizes, I have to write both of them out. So that's my, excuse me, that is my 10% condition. And my last condition that I need to check is success fail. So that's, is the population normal? Is the sample size big enough? Are there no crazy outliers or skew? So both of these sample sizes are definitely less than 30. The calcium one is 10. There's 10 people in that group. The placebo one is 11. You're not checking this against the total number of people in the study. It's for each group, right? Because I want to make sure that each group has an okay number of people in it. So they're both less than 30, which is no bueno because they didn't tell me anything about the population. I don't know if the population is normal. But again, if you take a second to graph this data, there's no crazy outliers or skew. I know that there are some pretty big numbers and some pretty small numbers, but if you graph all of them out, none of them show up really as outliers on either side, and there's no skew. Same thing for this one, right? We have like the -11 and the 12. Those might be outliers, maybe, but they balance each other out and it doesn't provide any crazy skew. So you're fine for this one. So I'm good there. I've checked all 3 of my conditions. Okay, so I'm almost done with the precursor part, right? The before you get to the math. So the last is my part before I get to the math is the end step, which is name the test. Remember, you are always asking yourself, how many samples am I dealing with? So it's 2 here. Is it Z or T? This is T because it's means. Remember, Z only goes with proportions. T goes with means. And then is this a test or is it an interval? And this is a test, right? Because they told me to carry out an appropriate test to find out. Okay. My advice to you for the actual AP test, if they don't say one way or the other and they just say, does the data provide convincing evidence? A test is going to be much more convincing evidence than an interval is, right? So typically if they want you to do an interval, a confidence interval, they will say construct a confidence interval. Okay. So for my end step here, there are 2 samples. This is a 2 sample, and then this is a t-test. Remember, again, you could have also said 2 mean t-test. Either would be fine. Okay, so that's all my precursors. So now on to the math. All right. Oh, wait, before I go on to the math, I always forget to do this up here. Like, I'm your statistics teacher, and I always forget to do this up here. I need to remember to set my alpha value up here. So I set it as 0.05 because they didn't give me a significance level at the top. If you look up at the top, there's nothing up there. It just says carry out an appropriate test. So 0.05 is your default if they do not give you an alpha value. All right, so now I'm on to the math. This is kind of an obnoxious problem because they didn't give me the summary statistics again. So I need to enter them in my calculator. So I'm going to move away from here and go over to my calculator. Whoops, it's not up. Oh, it's like me and my dad. How cute. Okay, so here's my calculator. I have already put this data in here, right? So I have CAL for calcium, right? And if you scroll down, there's my 10 values, and PLA stands for placebo. So those are my 2 sets of data. So I'm going to give you a second. If you have not already done this, pause the video real quick and enter all of the data into your calculator because we need to run 2 variable statistics on this. All right, so I'm hoping you pause the video and you have all of your lovely data and it looks just like mine. Yay, very exciting. Okay, so this is a 2 sample test. So you can run 1 variable statistics if you want, but you will have to do it twice. So I would recommend, just to save time, do 2 variable statistics, right? So you only have to do it once. So press your menu button, statistics, stat calculations, and then I want 2 variable statistics right here. Okay, so my X list is calcium, CAL, and placebo is my Y list. What I want you to notice here is if you watch the last video, see there's CA and GV. Those are from the confidence interval that I did. This is why it is very helpful to label your columns so that you know what you're dealing with. And it's easier to pick out when you do this in your calculator. Everything else stays the same. You just have to select your X list and your Y list. So then I'm going to press OK. Oh dear. Whoops. I forgot that you cannot run 2 variable statistics when the sample sizes are different. Whoops, that's my bad. So this is very annoying, but we're going to have to run 1 variable statistics twice. Sorry about that, y'all. I completely forgot about that. So sorry, go back. That's what that mismatch error was, the dimension mismatch error. The calculator doesn't like that. So sorry, we're going to do 1 variable statistics instead. So statistics, stat calculations, 1 variable statistics, number of lists. I'm going to say 1. And then I'm going to do this on each one individually. So this is calcium, CAL. So there's my values for calcium. Remember, I want X bar and SX. That's all I need. Okay, I don't need anything else. All right. And then I'm going to run it one more time on the other data set, the placebo. So statistics, stat calculations, one variable statistics, one list, and my X list this time is placebo. And then there's my result column. Okay. So here is my value right there. This does not look right to me. This number does not look right to me. So give me 1 second, y'all. Let me pause this because I think I entered my data possibly incorrectly. 1 second. All right, there we go. So I was able to fix it. Sorry, I ran this test beforehand. And when I did it the second time, the number was not right. I realized that one of my numbers, I forgot to put a negative sign in front of it. So that messed with my data. All right, so here's my one variable statistics for the placebo group. I have my standard deviation down here, the SX, and then I have my X bar. Remember, those are the only two things that you need. So let's go back to our test and let's actually run that. So again, I have all of the numbers and everything written out for you on the left, but I think it is helpful to see it written out live. So I'm going to do that for you here. Okay, so I have my two X bars. Okay, so X bar for calcium was exactly 5, which works out kind of nicely for us. And then I had X bar for the placebo group was negative 0.273. And then I have my standard deviation for both of those. So standard deviation for my calcium was, oops, it was very badly written. Let's try that again. So standard deviation here was 8.743. And my standard deviation for the placebo group was 5.901. And it makes sense that these numbers would be pretty big. If you look up at the range of numbers for calcium, see how it ranges all the way from positive 18 down to negative 5. So pretty big standard deviation there. And the placebo doesn't range quite as much. It's a little bit more balanced. Okay. And for this one, I do want to record what the N values are, the sample sizes, because they are different for each. So the sample size for calcium was 10. And the sample size for the placebo was 11. That's going to affect which one I choose for my degrees of freedom. So because the calcium group is the one we know the least about, it's the smallest group, that's the one I'm going to use for my degrees of freedom. So my degrees of freedom is 10 minus 1, which is 9. And I'm going to write that out over here on the side. So degrees of freedom here is 10 minus 1, which is 9. All right. And then my statistic. So in order to get my statistic, I need to do it in the same order that I did, that I wrote my hypothesis. So I did C minus P up here. So that's exactly what I'm going to do here. So my statistic is 5 minus negative 0.273. So that is 5.273. So that's my statistic. I realized that I wrote this as O and not T. Sorry. Let me switch that. I don't know why I wrote that. Because this is your test statistic, right? The goal of this step is to get the T value, because that's what you plug into your calculator. So there's my statistic, and then I need my new standard error, which is that very long and fancy equation. So it's a standard deviation of the first group, so 8.743 squared divided by the sample size of that group, which is 10, plus, and then I need to repeat it for the placebo group. So this was 5.901 squared. Remember, we're squaring these because we need to deal with variances here. You never add standard deviations. You always add variances, then divided by 11 because that's the sample size for the placebo group. So when I plugged all of that into my calculator, I got 3.288. So now I can use this to find the t value, which is this, the statistic. So 5.273 minus the parameter, which is this up here. It's always what your null hypothesis is equal to. So 0 divided by the standard deviation, which is this number that we calculated with the long fancy formula, 3.288. And when I plugged all of that into my calculator, I got 1.604. Okay, so just as a reminder, you don't need to use the t-table for this. You're calculating most of this by hand. And I am going to post a video for you guys a little bit later that shows you how to get the calculator to do a lot of this math for you. You will have to note, like it'll run the test for you. So it'll do a lot of this math for you so that way you don't have to write it out by hand, or you don't have to do it by hand. So that way you're less worried about having issues like I did at the beginning, where I typed a number wrong into my calculator. So stay tuned for those. I am going to post those a little bit later. Once I make those, I am going to show you how to do that on your calculator. Okay, so that's my T step. Hold on, pause. Someone's trying to come into the room. Hold on, pause 1 second. Sorry, y'all, that was my mom. Yeah. She just wanted to make sure I wasn't, like dehydrated or whatever. I've been recording videos for a hot minute up here. Okay, so where were we? We just figured out our T value. So that's, remember, what we use as one of our boundaries in the calculator for the O step. So I got to switch back to this. So O stands for obtain p-value. So that's what comes next. So this is the part where you need to switch over to your calculator. But before you do that, make sure you write the probability notation. So we are trying to find the probability that mu c minus mu p, how likely is it that that we get this sample, that this is greater than 5.273. All right. Another way that you can write this is hold on 1 second. I'm over here hardcore struggling. There we go. I wanted you to be able to still see the hypotheses when I wrote these. So you can write it this way, or you can write it with t, which is why we calculate the t in the first place. So what's the probability that I get a t value this extreme, 1.604, or more extreme? And notice that I use the greater than symbol. The reason I did that is because I had greater than in my hypotheses. All right, so now I'm going to switch back over to my calculator. So I need to add just a regular calculator button, or a regular calculator screen. So here's your steps. Okay, so I'm going to press menu, statistics, and then I want distributions for this one. Okay, but do you see how you have a confidence interval menu and a stat tests menu? So look, here's confidence intervals. So you have a Z and a T, two sample, proportion. And then for tests, see how I have all of these tests? Z, T, two sample Z, two sample T, one proportion Z, two proportion. These are chi-squared right here, which are not on the AP test this year. So like I said, I am making you a calculator video that has all of this stuff in it. what this will do is on the math step, it will do a lot of that math for you. You still have to write out the formulas because the statistics readers, the AP readers know that your calculator can do most of this math for you. That's why only about 25% of your points on these free response questions that deal with confidence intervals and with tests, hypothesis tests, come from the actual math. Most of it comes from your hypotheses, right? Your correct hypotheses, your assumptions, and then your conclusion and context, because that's not something that your calculator can do for you. All right. So again, stay tuned for that. But for our purposes, we're going to distributions, and this is T. So we are going to T CDF, right? Not PDF, CDF. So I have lower bound, upper bound, and degrees of freedom. So if I go back to my data here, what I'm trying to find is the probability that T is greater than 1.604. So I'm shading above 1.604 if I sketched this out. So I'm going to sketch it out for you all up here. Oh, that's really bad. Let's erase that. I've been struggling on this program with straight lines. So here's this. Here's my normal curve. Here's the middle, which is 0, right? And my T, this is 1.604, and I'm shading above. So 1.604 is my lower bound, and then I'm going to type in a bunch of 9s for my upper bound. So my lower bound is 1.604, and then just type in a bunch of 9s for your upper bound, and your degrees of freedom, we already said was 9. I'm going to press OK. And there's what I get, the 0.0716. So that is this probability right here, 0.0716, which is greater than my alpha value. I have run out of space on my screen, so I'm not going to write the rest of this out, but I do have the other 2 steps for you on this side of the screen, on the left. So let's go through those. Because my p-value is greater than alpha, right? What that means is that up here in my shading, so my alpha value maybe was right here, for example. So this didn't quite reach the threshold. It's not extreme enough. So I can't reject my null hypothesis. So here, because it's greater than alpha, we're going to fail to reject the null. And then you have to go through and write your conclusion and context. So because the p-value is greater than alpha, we fail to reject the null. And there is not enough evidence to support HA, the alternate hypothesis, which states that the true mean difference of blood pressure decrease, so that's your parameter, true mean difference of blood pressure decrease for the calcium and the placebo, is greater than 0. In layman's terms, what this means is we can't say that the calcium supplement reduces blood pressure more than the placebo. So we don't know if this medicine actually works well enough to reduce blood pressure. So that is your entire 2-sample test. The very last thing for this problem is this interpretation of p-value. See it right here? It says interpret the p-value of this test. So this is something that people get wrong a lot in the way that they interpret these. So I wanted to add it in for you one more time to remind you how to interpret a p-value. It's the same for every single test, no matter what, whether it's means, proportions, doesn't matter. The interpretation of the p-value is the same. Okay, so what the p-value actually is, this probability, is it's this blue shaded region that I have for you up here. So we're saying, because we ran this test, assuming that the null is true, there is a point. Oh, sorry. I realize I didn't change this from the last one. So this should say there is a 0.0716. So the probability, the p-value you got, there is a about 7% chance or probability of getting a difference in mean blood pressure reduction of, and then you put your t-value, not your t-value, my apologies. You put your statistic. So it's this one, the 5.273. right? For the two groups of 5.723 or greater just by random chance, right? So we're saying if it was any other random group of healthy Black men that we divided and did this study with, the chance that we would get this value of a statistic, the 5.273, that extreme again, or even more extreme, how likely would that be? And the likelihood of that is about 7%, which is pretty low, but again, not low enough to say for sure that we can reject this null.